So we've seen that ANOVA can be used to compare any two models, and to demonstrate the flexibility of the ANOVA framework, we can ask it. We can ask. So we've seen that we can make a linear model where you have categories like these different genotypes or categories, or you can consider this as dose, which is a linear regression, right, where you'd have 0, 1, or 2 of the minor allele of the little case a allele. So we can actually use ANOVA to say, is there a difference, statistically significant difference, in how much these two parameters, in how much these two models explain. So we're going to compare a 3-parameter model to a 2-parameter model. Okay, so the 3-parameter model, you remember, is this model, right? And so in this case, the genotypes, right? We have our data, and the genotypes are strings, right, which are factors. So you have these 3 categories. They're not ordered in this model. They're just 3 different categories. And then you just say linear model my data genotypes, right? And graphically, this looks like this. We have our three alleles, right? And these are the data that's associated with the allele. And the data can be anything, right? It's the weight of the mice. It's whatever your Y data are, right? And so we want to compare this model, which will be our full model, to a reduced model, which is the linear regression. Right? And the linear regression has just 2 parameters, the slope and the intercept. Right? So the data are the same, but we have the slope and the intercept. Right? So we just grind through, right? It's, again, the beautiful thing about this ANOVA framework, any 2 models you want to compare, you can grind through with the same infrastructure. Right? So here's the model with the three alleles, right? That are encoded as alleles, right? So they're factors. So the alleles are big A, little a, and little a, right? And this is the sum squared error, the residuals associated with this model. Here I have the same framework, but now I'm representing the data as dose of the little a, right? So I either have 0, 1, or 2 of the little a's, right? So 0 if it's big A, 1 if it's 1a little a, or 2 little a's, right? I just rebuild the model, right? Replacing, instead of having genotypes, I have numbers. I rebuild the model. And I get the residuals here, and then I just grind through my formula, right? So reduced error minus full error divided by the reduced degrees of freedom minus the full degrees of freedom. Well, there's one difference in degrees of freedom between these models. This is a 3-parameter model. The parameters are 1, 2, and 3, the means of each category. This is a 2-parameter model. The parameters are the slope and the intercept, right? So the difference between the 2 models is 1 degree of freedom, right? Because this is divided by 1. So I take this difference in the residuals divided by 1, and that's the numerator of my F statistic. And then, of course, the denominator is just the full divided by the full degrees of freedom, right? And there are 21 data points in the data set. There's 3 parameters in the model, so it leaves 18 degrees of freedom. So we take this ratio, and that comes out to this number. And we say, okay, is that PF, we'll evaluate the statistical significance of this using the cumulative F distribution at 1 and 18 degrees of freedom. 1 and 18 degrees of freedom. And so here, it's not, if we use a 0.05 threshold, it doesn't make a difference, right? It's 0.07. So maybe it makes a little bit of difference. But the 3rd parameter only makes for a marginally better model. And that kind of makes sense here, right? Because you can sort of model this as a line, right? You can kind of model this as a line. So you can see that it really doesn't make a difference to have 3 parameters versus 2 parameters. But let's consider a different data set. Let's consider a data set that is not as well matched by a line. So here I just changed the data. I'm going to do exactly the same calculation, but I just changed this data. So clearly now a line is not going to be able to fit this data very well, right? So if I had 3 means here, I'd have a mean here, a mean here, and a mean there. That's clearly going to be a much better fit than a line, which doesn't hit any of these guys now and misses most of the other guys too, right? The line is trying to split the difference between the low guys here and the low guys here and the high guys here, and the line doesn't get very close to any of the data points. So now I do exactly the same thing. I do exactly the same calculation, just substituting it on the new data, right? So here's my 3-parameter model, big A, little a, big A, little a, and little a, as factors, right? And the residual sum squares comes out to this number. And then here's my 2-parameter model, and now the error jumps considerably, right? Because most of these data points are nowhere near our 2-parameter model. So the error is much higher. And when I just grind this through the same formula into R, right? So this number minus this number divided by the difference in the degrees of freedom between the models, which is 1, divided by the full error, divided by 18 still, right? Now I get this. And now when I say, is there a difference between the 2 models, I reject that null hypothesis very, very strongly, right? So clearly this model, where I have means for each one of these data points, is much better than this model. So this is actually going to be your homework this week, is I'm going to have you, for each data point in the RNA-seq data set, I'm going to have you fit a 3-parameter model, right? So remember that our RNA-seq data set had 2 days, 12 weeks, and 18 weeks. So for each one of the genes in that model, I'm going to have you fit a 3-parameter model, a 2-parameter model, and then look at the difference between them and report all the p-values that are significantly different between those models.